Let us now go to the next data model, tables. So table is associated with a tabular signature. This is a sequence of attributes. A, like for courses, we have the name, number of credits, description, and so on. And DOM. DOM is the sequence of a domain. So we have a sequence of attributes and attributes, A1 to AN, and domains. Okay. And domain is basically the space of values from which the attribute can take its value from. And it can be finite, like yes, no, or infinite strings, numbers, and so on. Okay, and so we write a DOM of AI to refer to the ith domain. Now, a table or a relation over this tabular signature T is simply a finite subset of the Cartesian space of the domain, just a table. Okay. And do note that we use set semantics. So we do not allow, for example, duplicate tuples in our representation. And every tuple in this table R is called well, we call it a tuple. We can call it sometimes a row and sometimes a record. Okay. Now, we use this notation for projection. So we have a tuple A1 to AN, and we refer to each value AI as T dot AI. AI is the attribute name, or we put it in brackets like that. And if we have a sequence of attributes, B1 to BL, then we write like T with this sequence of attributes to denote the tuple that is obtained by using only the values of the attributes in B. Okay, so this is basically the projection of the tuple T to B. That's all. These are the tables. Now let's go to the relational databases. So our model of a relational database is based on the idea of a schema. Schema gives again the structure of the meta information. What do we see in a schema? So we see here the different tables that we have. Each has a name. Um, and some of them here have a key specified with the underline. They have their sequence of attributes, like in a table or a tabular signature. So we mark it here as a sig of the relation name. What else? We see here that there is a reference. So the schema tells us that this SID references the SID of a student. So we call it a foreign key, and we mark it in this way. Take of SID is a subset of, we use this square containment symbol. Take SID is contained in the key of student, and the same we have for CID with respect to a course. That's the idea. A formal definition. So a relational schema consists of R, C, key, FK. R is a finite set of relation names, okay, student, courses, and so on. Sig maps every relation name to its corresponding tabular signature, okay, the sequence of attributes. Key tells us what is the primary key, or the key, right, the underlying part of every relation R, relation name R. Okay, and this is a sequence of attributes from the signature of R, and FK is a set of foreign key constraints. I'll define them next. And so the formal shape, okay, or the syntax of a foreign key, the formal syntax looks like that. RC contained in key of S, and we use the square containment. And here, R and S are relation names in R. C is a sequence of attributes from the signature of R. And it is important that C and the key of S have the same length, okay, so that one can indeed reference the other. and say we sometimes can say that R doesn't have a key, but that doesn't mean that the key is empty or something like that. It actually means that the key consists of all of the attributes. It doesn't say much. It just says that we don't have the same tuple more than once, and we assume that this is the case because we use set semantics. Okay, again, this is different from saying that the key is empty. But we think of what does it mean to say that the key of a relation is empty. How many tuples can such a relation have? Okay, so if the signature is a comma dom from for one of these relations is a tabular signature. So we denote by dom of R essentially the domain of the tuple of the table of R. Okay, and again, this is the Cartesian product of the different domains. Okay, so we defined schema. Now, what is a database? So if this is our schema, RC key FK, then a database is what we expect it to be. It maps every relation name to an actual table, and we mark it like D of R. If D is our database, then we mark this table as D of R, and this is a table D of R over the signature of R. Yes, as expected. Okay, and of course, primary keys are respected, which means that for every relation R, we cannot find two distinct tuples, T1 and T2, that have the same key. Okay, different tuples should have different keys. And also, foreign keys are respected. What does it mean? That if we have this constraint R of C contained in key of S, okay, this is one of our foreign keys or foreign key constraints, then for every tuple T of the relation of R, of the table of R, we can find a tuple S in the relation of S in D of S, such that they agree on the values. T of C is equal exactly to S projected to the key of S, exactly as we expect it to be. Okay, so here, for example, SID is a foreign key to a student, and it says 89, and indeed we can find a row here with the SID 89. Okay, and here we have a 25, and indeed there is a 25 here. It doesn't mean that every course ID or occurrence of a key should have someone that references that. Okay, this 34 here, nothing references that, and this is fine. What's important is that every CID that is a references something that is real. Okay, now we also use this concept of a fact. Okay, a fact is similar to a tuple, but it also tells us what is the name of the relation. So if we have a table D of R and we have a tuple T inside it, so this expression of R of T is called a fact, and this is a useful concept. We'll see that later. So for example, if we have the tuple 89, 12, 20, 25, 1, and this is a tuple, then take of this tuple is a fact, and we often can identify or associate the database or view the database basically as a set of facts. We can say, one database is contained in the other if a relation of the first is contained in the corresponding relation of the second.